Hello everyone. So today's video is about gradient descent. We will first learn what gradient descent in general terms is. As you can see, gradient descent is an algorithm to minimize any function. When we have to find the possible minimum value of a function, we use gradient descent. As you can see here in this graph, there is a function in which we have to find the minimum value. Here, this value is the minimum and gradient descent helps us to find this value. But how do we use it in training machine learning algorithms? For this to understand, we will learn basics about linear regression first. So in linear algebra, what we used to do is we have this equation and x as an input. And with these values of x, we have to compute the values of y's. This y is the result with x as an input. How this 5 comes? We take one input in this equation. 2 into 1 is 2 plus 3, 5. And that's how we calculate the value of y. But in case of machine learning, however, you have observations instead of equation. We try to derive the equation with the help of input and output. This x is the input and this y is the output of this input. Like 5 is the output of 1, 7 is the output of 2, and so on. So we try to derive the equation that looks somewhat like this. So now coming back to the problem of house price prediction, we have been given area and price. Based on the area of the house, the price is listed here. Like the price of a house whose size is 500 feet will be around $100,000. So we will try to derive an equation through area and price. Area will be used as an input and price will be used as a predicted value of that equation. Price is equals to m into area plus b. By determining the value of m and b, we can determine the price of the house whose area is not listed in this list of inputs. We will try to plot these data points in a graph. Size is the independent variable and can take any value, and the price is the dependent variable. Price is dependent on size, so I have plotted size on x-axis and price on the y-axis. Our goal is to obtain the previous equation and by determining the correct values of m and b. So we will try to draw a line that passes through these data points. The data points are scattered, so it is not possible to draw the perfect line, but you can try to draw a line which is kind of a best fit. But the problem is you might have different lines that can pass through this set of data points, like one line, this, there can be multiple lines that can be passed through these data points. If you have a large data set that is even more scattered, it is even more difficult to draw a line. And the equation of this line will be y is equals to mx plus c, where m is the slope of the line and c is the intercept of the line. Y will be the price and x will be the area. X will take the values of area and y will be used as a predicted value that this equation will predict. So now how do we determine which line is the best fit? One way is to draw any line by initializing random values of m and c and then calculate the error between the actual value and the value predicted by the line. As you can see here, the house with size 500 feet, its actual price is $100,000, but the price predicted it to be somewhere around $150. So what we will do is we will just calculate the difference between the predicted value and the actual value is equals to 50. And we will calculate this error value for all of the data points and then we will just add them. We can also represent them by y predicted minus actual value and then we will square them. The reason we are squaring them, because if the error value is if the error difference is negative, and if you just simply add it up, then the result will be skewed. So we will add them. I is equals to 1 through n, and then we will divide it by total number of data points that we have, and this is known as minimum square error. So the equation that I just previously explained is the cost function for the linear regression. You calculate the difference between the predicted value and the actual value, square them up, add it up for all the data points, and then divide by number of the data points that you have. Now this equation, this value of y predicted is replaced with mx plus c, because we know the equation for straight line is y is equals to x plus c, and the final equation generated for the cost function of linear regression is this. So as we have previously discussed, that there could be multiple number of lines that can be drawn by changing the values of m and c that can pass through the set of data points. So we have to choose the best fit line, and the best fit line will be that line that gives us the minimum value of the error, that the error value that has been calculated through this equation. So we draw different lines by changing the value of m and c, and we will see on which value of m and c it gives us the minimum error. But now it is not possible for us to consider every value of m and c and then calculate this equation and then ultimately calculating the error. It is not possible for us, right? Fit line. So now we use gradient descent for finding the best fit line in a very less number of iterations and in a very efficient manner. So, in the beginning of this video, I told you that gradient descent is an algorithm that is used to find the minimum value of a function. In the linear regression, the function that we have to calculate the minimum value of is the cost function. In linear regression, the cost function squares the error and ensures that the error surface is convex like a soup ball. It will always have a minimum value that can be reached. As you can see here, if you iterate the values of different parameters w and c, you will find here will be the minimum value of the function. We have to find this value through different iterations of the gradient descent. This is a 3D graph because two parameters are used, theta 1 and theta 2, as you can see here. They are nothing but our m and c that we used in the linear regression equation. To simplify it and to understand the gradient descent much better, we will use a 2D figure where v is the only parameter and the cost function depends only on the v. In this 2D graph, we see that the minimum value for cost function is here. So if we initialize the value of our parameter to be here, the value of the cost function, as we can see, is not minimum here. So the gradient descent will iterate through every loop and will try to reach the minimum value of the function. In the first iteration, the value of the parameter will be this, then this, and somewhere it will reach to the minimum value of the v, that is the minimum value of the cost function. So we have to calculate the value of w and b to find the minimum value of the cost function. So in other words, we have to optimize these two parameters w and b to minimize the value of the cost function. And how do we do this? With each iteration, the value of w will be reduced or will be increased. That will depend on the derivative of the cost function. If the derivative of the cost function is negative, we will add the value, and if the derivative of the cost function is positive, we will reduce the value of w. We will see it later how it works, but for now you have to understand this equation, that with each iteration the value of w is reduced. Alpha here is the learning rate which determines how big step is to be taken. and repeat it until it reach the local minimum. So now this derivative is nothing but the cost function, a tangent actually drawn to the curve that determines the direction in which we have to go. Like for example this, if we have our value of the parameter w here, we have to reach the local minimum by reducing the value of w. But how do gradient descent does it? It does it by calculating the derivative at this point. Suppose we have the value of w and we have plotted here. It will draw a tangent to this point at the curve and will calculate the derivative. The derivative will be calculated of the cost function with respect to the w. And when the tangent line is pointing up and is on the right side, the tangent line is on the right side, the slope, that is dj by dw, is positive. So now the equation w is equals to w minus learning rate into something positive. If the derivative is positive, the learning rate is always positive as it is a constant. So w minus this positive value. So the updated W will be less than the original W. So if you see here, the W was here and we have to go through and we have to reduce the value of W. So if the next updated W is here, so this will be the new W in the first iteration. Then in the next iteration, again the same thing will happen. We will draw a slope at this point and we will determine the direction in which we have to go, in which whether we have to reduce the value of w or we have to increase the value of w. And then again through this equation we will calculate the value and we will reach the global minimum with each iteration. The next case is if we have initialized the value of the parameter to be somewhere around here. Now, reducing the value of w will eventually increase the value of the cost function. As you can see in this graph, if you reduce the value of w, if the value of w is reduced at this point, then it will increase the value of the cost function, right? So what we have to do is we have to increase the value of w so that we can reach the minimum value of the cost function. Now, if the tangent line is on the left and is pointing downwards, the slope is negative. So the direction of the slope is negative, the direction of derivative is negative, and learning rate is always positive. So negative into negative is positive and the updated W will be greater than the original W. So in the first iteration, if the value of W is here and in the next iteration, the value of W will increase. So the value of the cost function will be here. And we have to go downwards in order to reach the minimum value of the cost function, that is here. Now there is also a condition for the learning rate. If you choose the value of learning rate to be very large, you might miss the local minimum point. I'll show you how. Suppose this is your cost function and the value that you have initialized is here. Now, if you choose your learning rate to be a very large value, you might miss the local minimum point. You're going here, here, and with each iteration, you're going downwards. You're going in the same direction, but what will eventually happen is if you are at this point and if the value of learning rate is much larger, then this might happen. The value of the local minimum is skipped because you chose the value of learning rate to be much larger. It skipped the minimum point here. So that's why we have to be very careful for choosing the value of learning rate. The value of learning rate is not fixed. You can take any value like 0.01, 0.001, and can test it by checking the accuracy of the model. It will be discussed later. Now, how the gradient descent will know that the minimum value of the cost function has been reached. If you see here in this curve, and at this point, the slope of the line is calculated and the slope of the line is turns out to be 0. So put it in this equation, w minus alpha into 0. This term will be 0 and w minus 0 is w. So there is no change in w. When there is no change in w, it means that the function has reached its minimum value and the gradient descent can stop its iteration to find the minimum value of the cost function, and that the parameter w has been optimized, that at this value of w, the cost function will be the minimum. So now we will talk a little about the derivative that we have been talking about in the equation that was used to optimize the parameters w and b. Here in the cost function, the derivative was dj by dw. This was the parameter, this was the derivative that was used to optimize the parameter w, and dj by db is the derivative that is used to optimize the parameter b. So we will calculate dj by dw and dj by db separately. This is the cost function that we have discussed, and this is the final value by replacing the y predicted. This y hat is the y predicted value and this y is the actual value. These are just different way of representing the variables, so don't get confused. And when we calculate the derivative, I'm assuming that you know the basic rules of derivative, how we calculate the derivative and what are the basic rules for calculating the derivative. If we are calculating dj by dw, since it's an equation with two parameters like w and b, so it will be a partial derivative. You cannot fully compute the derivative, so we will use the partial derivative, and the equation after computing this will be this equation. It will be used in the implementation of gradient descent. So if you don't know how we get this equation, you can just look it up and use that equation in the code. Don't worry about it if you don't know. Then similarly, same with this dj partial derivative of cost function with respect to b, this equation will be this. So that's enough for the theory part, and now it's time for the implementation of gradient descent. We will implement the gradient descent in Python, and the platform that I'll be using is Jupyter Notebook. So I will show you step-by-step instruction on how to implement gradient descent. Which takes two parameters x and y as the argument, and then in the previous slides we have seen that we have to initialize some random values of the parameters w and b. So w current is equals to b current is equals to 0. So I'm initializing it with them with 0. Then we have to specify the learning rate. I'm taking it as 0.001. Then we have to mention the number of iterations that the gradient descent will go through. So 1000, and n is the length of, yes, so it is the number of data points. Now for I in range iterations, this is the for loop that will iterate every value of the iterations. it will run 1,000 times, and then uh, y predicted. This for loop basically means that the value of parameters w and b will be iterated 1,000 times. So y predicted will be from the equation y is equals to wx plus b. So w current into x plus b current. Now we have to calculate the cost function for these values of w and b. So cost is equals to 1 by n into sum of value into 2 for value in y minus y predict. So this value is the error value that has been squared, and this is the value of error, and we have to store it in a value val variable, and then we square it and then sum it and then multiply it by 1 by n. Now we have to calculate the w derivative. This is calculated from the equation that we solved from the calculus rules, and the same will be calculated for w and b. So change it with b, except that it is not multiplied by w, and you can check the equation for w derivative and b derivative, and this you will get. Then you have to update the values of w and b by w current minus learning rate into w derivative, and the same way you have to update the value of b. Yes. Now you have to print these values so we can see how well the cost function and all these parameters are giving us the values. So this line will print the value of w, b, cost with its cost, that what the cost of the function is when the value of this parameter is used. So that's it. That's how we define the function of gradient descent. Now we simply run it, and now we have to pass two vectors that will be used in this function. These for this x and y. We need to define this now. So x, I'm gonna take np dot array, and y np dot array 5 7. That is the same example I used in the beginning of this video. So run it and now pass it to the gradient descent. Yes. So here you will see that there are 1,000 iterations with the different cost when different values of the parameters are used. There are total 999 iterations starting from zero. Yes, starting from zero. So there are total 1,000 iterations, and the cost is specified with each of the value of w and b. So from this you can get the idea how when changing the parameters, when changing the value of these parameters, the cost is getting affected. So that's for the video. Thank you.